morning, everybody. Thank you for coming to this, not last, but almost the last seminar of the year. I want to introduce you to Peter Sudhölter. He comes from the University of Southern Denmark, and he's an expert in cooperative game theory. And he's going to talk us about characterization of the core on convex games with and without consistency. So thank you, Peter, for coming. This is the twice time that we have the honor to have you here, and I hope it's not going to be the last.
Thank you very much
Thank you very much
for your kind introduction. Indeed, I have been here, and I can look at it on November 28 in 2017. So maybe some of you were there. This I don't remember, but I remember that I talked about core stability. What that means, I tried to show you when a game has a core that is a stable, a von Neumann-Morgenstern stable set. Very complicated and sophisticated paper that has now been accepted by published by mathematical programming. Today I will talk about something that is also related to the core, but it's all things are a little bit easier. They are easier to understand, I hope, at least. So let me directly start. So I have this kind of survey talk, and I don't know how long it will take, maybe 40 minutes or something of this kind. Let me try to tell you what I'm doing. So there are two manuscripts that I should like to introduce. On the one hand side, if you have a characterization of the core, so this is the axiomatic approach. If you have a characterization of the core, it's not clear whether the same axioms are also applicable to smaller sets, whether they are valid, and also whether they are sufficient to characterize something, or to increase the set is also not automatically possible. And we are dealing with a situation that we consider only convex games, and look whether classical characterizations are also available for the restricted set of convex games. And this is joint work with my Japanese colleagues Hokari and Funaki. And on the other hand, there is a character. So the core is typically characterized by consistency properties. So you need to be able to change the size of the population. But the Shapley value, for instance, the classical characterization of the Shapley value is on a fixed set of players. And then we ask ourselves, is it possible also to do this for the core? So can we restrict our attention to the core of games that have a fixed player set, and then can we do something there? And at least for convex games. So this is the other paper that I should like to briefly present. This is joint work with my French colleagues Vial and Gonzalez and Solal. And let me also tell you that you have to ask, if you want to ask, please interrupt me whenever you would like to interrupt. So I must get used to it. Let me try to introduce a little bit to motivate what we are doing. So there are classical characterizations. The first one is due to Pelek on the domain of balanced games. He characterized the core in '86. On this occasion, he introduced the set-valued version of consistency of the reduced game property. And later on, Tadenuma did a similar axiomatization using another reduced game. And formally the paper in '85 is earlier than the one in '86 on the characterization of the core for games that have a non-empty core, for non-transferability games that have a non-empty core. And then there was an axiomatization of the core for totally balanced, for market games, for totally balanced games in '86, and then Pelek noticed that in the proof there was something not clear, and he weakened the result, and in 2002 we could reprove the original result. Therefore, I have also mentioned in this context here. There are also more recent articles. I don't want to be exhaustive. I don't know how to be exhaustive in this context. Vornefeld and van den Nauweland, they used another version of the Davis-Maschler reduced game. Serrano and Voli, they employed a very strong version of the converse reduced game property that allows them to characterize the core on in multiple situations, for NTU games, for TU games, and for multiple economic situations. And then Wang and myself, we introduced the reconfirmation property that I will not talk about, which is another consistency property. So the core satisfies, with respect to the Davis-Marshall reduced game, 3 consistency properties. And the reconfirmation property is very useful to characterize the core on the class of all games, even if the core is empty, on several subclasses, super additive games and balanced games. So it's very suitable for this kind of characterization, also for non-transferable utility games. And then Albert Suri and myself, we tried to repeat the classical characterizations for a larger class of games, for TU or NTU games with communication structures a la Meyerson. And this also works. Most of the characterizations can be carried over to games with communication structures. So let me give you a few further results about reduced games. So I'm only talking about the so-called Davis-Marshall reduced game that is called now Max reduced game in the literature, and about the reduced game introduced by Muller, which is now called complement reduced game. This is used in the Tadinuma characterization of the core that I will show in a few seconds. There are also other reduced games, the subgame reduced game or the projection reduced game, and then Sobolev found a reduced game that is suitable for the Shapley value, and then there are self-reduced games, but the core does not satisfy consistency with respect to self-reduced games, at least not on a significant set of games. Therefore, we don't talk about this today. There are the following remarks. So, as I said already before, the reduced game a la Davis and Marshall is most suitable for the core, namely, and this for the core it has the following situation appears: the core satisfies the reduced game property, and the convex reduced game property, and also the reconfirmation property, but only with respect to Davis-Marshall reduced games. If you look at other reduced games that complement the projection reduced game or Sobolev's reduced games, Sobolev's, there is nothing satisfied, and for the others, at most consistency, at most the reduced game property is satisfied. And self-consistency is not satisfied at all. So the max consistency, the max reduced game is the most suitable reduced game for the core. Now the last remark for the moment is that the Shapley value, as I said, can be characterized without consistency. You need some standard axioms and additivity. Standard axioms and additivity characterize the Shapley value. This was the original work by Shapley. He characterized the value by 5 axioms, and therefore we have the following natural questions. So the natural question, the first axiomatization due to Pelec and Tadinuma, can do their work if we restrict the attention to convex games? It's a very small subclass of the set of balanced games. And the second question is it possible to fix the player set and to characterize the core without using any kind of consistency? And both questions I should like to discuss today. So let me start with preliminaries. So we have a universe of players, not to leave the set valued, theoretical context. You don't want to talk about universal algebra problems. I assume that there are at least 3 players are in the universe, because I will show you 3-person example. So we need three people in the universe of players, maybe more, maybe infinitely many, it doesn't matter. So at least 3 we need for the example. And then a transferable utility game consists of a pair. On the one hand side, the generic set of players is called capital N. You can think of players 1 to small n. And the generic collision function, characteristic function, is denoted by a letter small v. And it decides to each collision. A collision is a non-empty subset. To each non-empty subset, the amount of money that is available in this non-empty subset if the people cooperate in this set, and also to the empty set, by traditional reasons we assign 0. So the empty set is not a collision, but it's a subset. Then we need the notion of convex games. A game is convex if the collision function, the characteristic function, is supermodular, which means if the sum of the, we call this worth of collision is if the sum of the worth of 2 collisions does not exceed the sum of the intersection of the worth, the worth of the intersection and the union. And we know the set of all games by capital gamma with a lower index capital U, and the set of convex games by capital gamma with a lower index U and an upper index vex. So this is the notation, and then vectors or proposals or allocations can be seen as games themselves. So a vector in the Euclidean space, the coordinates are the names of the players, and we have a collision or a subset of n, then we denote by x of s the amount of money that is available in capital S according to the vector x. Also the restriction of s, x to s is denoted by x with a lower index s. These things we need, and then we can also have to say what is a solution. Solutions, or solution concept to be more precise, the generic letter is a sigma, a solution concept sigma, on a set capital gamma of games, of transferable utility games, assigns to each game under consideration, to each game NV in gamma, a set of proposals, a set of vectors that are affordable for the grand coalition. So the grand coalition has enough money to distribute the money. They can distribute the money according to the vector. They are allowed to throw away some money, but they can distribute the money according to the vector x. So this is a solution. So it can be self-valued. There can be many elements in the solution. For instance, one solution is the core. The core assigns to each game the set of all affordable vectors, of all feasible vectors that assign to each coalition at least the amount of money that is available if all people in the coalition work together. And it's easily seen, and you know this, that the core may be very big, maybe a big convex set. Sometimes the core is empty, so we don't have these kinds of restrictions. So the core is, if the core doesn't exist, we say that the game is a balanced game because there is the Bonder-Weber-Shapley characterization that says the game has a non-empty core if something is balanced. So we talk about balanced games, and otherwise the core is empty. So classical and traditional nice properties of a solution are as follows. There is first of all an economic property that is, so economists don't accept solutions that are not Pareto efficient. Pareto efficiency requires that each proposal exhausts the whole money that is available. And then I personally don't like solutions that don't satisfy non-emptiness, because if a solution is empty from time to time, then you don't have a solution for this game. I mean, this non-emptiness is a traditional property. Individual rationality required, this was applied in the 60s and 70s. Always it was assumed that everything is individually rational. It requires that a proposal to the solution is individually rational, assigns at least the amount of money that the individual has in its pocket to each player. Then there is super-additivity. Anonymity says the solution does not care, it's not depending on the names of the players. I put it here a little bit more formally. And then we have additivity. Additivity requires that if two games and their sum are all under consideration, then the sum of the solution of two games is the solution of the sum of the two games. And this sum means the Minkowski sum. So each element of this solution plus each element of this solution is a solution of the sum of the games. And super-additivity is a little bit weaker. It says that if the red inclusion is valid, so the sum of the solution is contained in the solution of the sum. Then we have scale covariance. Scale covariance only requires that if you measure the amount of money in a different currency, then this is taken into account in the correct covariant way. And then finally, we need at the moment the null player property. What is a null player? A null player is a player who does not contribute. So if he joins a coalition, then this does not change the worth of the coalition. And the null player property requires that each null player from each element of the solution receives always 0. These are not critical properties. So let me talk about reduced games. So reduced games are results of a Gedankenexperiment. So if people decide to, or want to decide to apply a solution or an element of the solution, then they ask themselves whether this is consistent, and for this they need to be able to reduce the society. So if some people go out and take their money, the proposed money with them, but they go out, but they are ready to cooperate nevertheless. They have only taken the money. Then the new grand coalition, which is now N prime, the new grand coalition, the money that is available is V of N, but they have to pay them because they have already taken the money. They have to pay the outside players according to X. The positive view of the world for other coalition is the following. The people outside are ready to cooperate. So S can ask any subset of outside players to cooperate if they are ready to pay them according to the vector X. And the maximum can be taken. This is a positive, optimistic view of the world. And of course, it's a Gedankenexperiment, because if you have two, for instance, disjoint coalitions, S and S prime, they may have to take the same kind of T. So it's not, you cannot play the game. It's only in your mind. And nevertheless, this is what is very famous and very famous reduced game, the Davis-Marshall reduced game. The subgame, the complement reduced game is even easier. You only look at the first line, so always the coalition has to take into account if the players, outside players enter and join, and then they have to be paid accordingly. This is a complement reduced game. And if we have these reduced games, according to which reduced game we apply, we need to define consistency properties. So either we talk about the Davis-Marshall, the max reduced game, or the complement reduced game, and then we say consistency, a solution is consistent if whenever we take a game, proposal in the solution and collision, then it must happen that the reduced game, be it like max or complement, must be a game under consideration. And secondly, the restriction of the proposal to the players in the room, that must be an element of the solution of the reduced game. Moreover, there's a weak version of it. This only requires reduction to 1 and 2 person reduced games. And then there's the converse reduced game property is the following. You start with a Pareto optimal proposal. X is Pareto optimal, so it exhausts the whole money. And you ask yourself, is this feasible for us? And then if the converse consistency says if whenever two people meet and they look at their reduced game, then it turns out that their reduced game belongs to the games under consideration, and that the restrictions that their two components belong to the solution of the reduced game. So if this is true for every bilateral situation, then the whole vector must belong to the solution of the game. This is converse reduced game property. And then we can repeat the classical results. So the core is characterized on TU games, on balanced TU games. And games that have non-empty core is characterized by non-emptiness, individual rationality, superadditivity, and the reduced game property with respect to the Davis-Marshall reduced game. And Tadenuma showed that complement consistency in this context is a little bit stronger, so you don't need anymore to assume superadditivity. And then there was this characterization by Pelec originally by non-emptiness and individual rationality, superadditivity, the weak consistency with respect to Davis-Marshall, and converse consistency with respect to Davis-Marshall. This was the original theorem in '89, and then it was detected on totally balanced games. Totally balanced games are market games. The market games and totally balanced games are the same. So then Pelec detected that there was a mistake in the proof, and he weakened the result. And in 2002 we could rescue the original result of the '89 paper. This was our result now of my Japanese colleagues is that Tadenuma, so that we don't know what to do with Tadenuma for convex games. The properties are satisfied, but even if we add the innocent property of anonymity, it is not sufficient to characterize the core. So there are many solutions satisfying these properties on convex games, which are not coincide with the core. For this result, it's a little bit better, and I tell you, we have a little bit a positive result. Here is a positive result, so I have to repeat for those who are not familiar with the relative interior of a convex set. I have to repeat that the relative interior is simply the interior of the set in its affine hull. So here is an example of 3-person, therefore I need 3-person. So I have again the grand collision receives 6 units, and the singletons receive at least 0. So here I have the imputation set. Imputation vector is an imputation if it's Pareto optimal and individually rational. So everybody receives at least 0, and together they receive 6. So this is the imputation set. The core must be a subset of the imputation set, namely it must be the subset that also has the inequalities. For instance, x of 1 and 2 must be at least 2. X of 1, 3 must be at least 1. X of 2, 3 must be at least 2. Here is the core. Here is the core. You see this line you receive. This is the point 330, 303. This you receive if you look at the condition that x of 2 plus x3 is exactly 3. So this line is this line of imputations in which collision 2, 3 exactly receives 3 units. And if you are on this side, then this collision receives more. And similarly, you receive a line here, a line segment here. You must be below this line segment because v of so x1 plus x2 is larger than or equal to 2. This is this part, and x1 plus x3 is larger than or equal to 1. This is this part. So the core must be this blue area. So if you have a line that connects 2 points in the core, so the affine hull of this. The core is, you look at all lines that intersect 2 points, for instance. This is so the affine hull is the whole plane, but it's not our space. So the core lives in the 3-dimensional space, but so the interior of the core is empty. The interior of the core, the topological interior of the core is empty, but the relative interior only says the interior in this plane. So you only have to take away the boundary lines. So you have only to take away the boundary lines and you receive the relative interior. So the relative interior of a non-empty compact convex set is always non-empty. This is what I'm saying. So this is the relative interior. Now I can tell you the result. The result is as following. We have the axioms that characterize the core for market games plus anonymity. So the axioms that characterize the core for totally balanced game plus anonymity. This is sufficient to characterize, almost sufficient to characterize the core. Only 2 solutions satisfy these properties, namely the core itself or the relative interior. We cannot avoid this. So we don't have a characterization of the core, but almost. So we have either the core or its relative interior. If we want to have the core, we can add, for instance, closedness. So if you have closed valuedness, then this rules out the relative interior of the core. So this is possible. In this sense, it's possible to keep the result of Pelec for a totally balanced game, almost, except we add anonymity. And of course, the axioms are, each axiom is logically independent of the remaining axioms in this characterization. So this is the end of this part. And now let us talk about unanimity first. So I go now to fix the set of players. So the player set is capital N, a finite non-empty set. And if we fix the N, then we delete it. So we write simply V. And then I should like to define the unanimity game on a collision. T is a non-empty subset of N. So T is a collision. The unanimity of the game on T assigns to each collision that contains capital T 1. And to each other collision, it assigns 0. This is all a unanimity game. There is a very classical game, so you need the total unanimity of all people in capital T in order to make a decision or something, to win. Otherwise, you lose, you receive 0 if not all people in capital T are members of the collision. And it is known by the result of Shapley that the unanimity games form a basis. By the way, if you want to express an arbitrary game as a linear combination of the unanimity games, when we receive the linear coefficients by a Möbius transversion. So they are easy to determine. So the unanimity games form a basis, and therefore every game is a unique linear combination of unanimity games, and this allows me to define positive games. A game is positive if all coefficients of the linear coefficients are non-negative. This is a set of positive games. So this is a very small subclass of the class of convex games, but a nice subclass. It has applications. I have one application. So the positive games are the extended highway games. So we have defined cost games for a highway. So it has an application. This is all what I wanted to say. And now we have the property of unanimity that I have to defend a little bit. So a solution satisfies unanimity if for each unanimity game under consideration and each player in the determining collision, you can move all the money to each player in the collision. And this kind of liberality is very similar to a property that was introduced by Preliminaries many years ago. You also call this property unanimity. We only consider two-person games, and in the two-person game context, he said, unanimity says, we can take any imputation, so we have the freedom to assign to the game any imputation. Here we do something very similar, only for unanimity games. They are so obvious, when you say have the freedom to assign the whole money to each player you want. So this is used to make the solution big. I mean, we have to pay for the fact that we cannot use consistency by something. And this is the axiom that is introduced in this context. This gives us immediately the following result. If we have a cone, what is a cone? A cone. So a cone. If you have two games in the class of games under consideration, and you look at the line through these two games, then this must be also no. I'm sorry. You have to look at the non-negative, not convex combination. You have to look at the non-negative combination. So if you have two games and you take a positive factor of the first game plus another positive factor of the second game, this must also belong to the game. Then you receive a cone. And we need that we have a cone. For instance, the positive games form a cone. The convex games form a cone. And if you take one game that is convex but not positive to this, and then we look at the positive combinations of this positive games and this game, then you have another cone. So you have a lot of cones in between. This is what I'm saying. And then the core can be characterized by Pareto efficiency, by individual rationality, by the null player property, by the unanimity property that I just mentioned, and by additivity. So for convex games, the core satisfies additivity, and this is very crucial. This is only for convex games. So if you add one single game, if you have a core, you have a cone that contains the convex games and one single other game, balanced or not, then the core does not satisfy additivity anymore. So this is very poor. For balanced game, then it does not satisfy additivity anymore. So this is very crucial that additivity only works for sets of convex games for the core. This corollary, if you want to get it bigger, then we can do the following. The core in general satisfies super additivity, but not necessarily additivity. So if we restrict our attention, if we want to characterize a core on the set of all balanced games, on all games that have a non-empty core, then it can take these axioms, all these axioms, except that additivity is not allowed because it does not work. We replace additivity by super additivity, and then we add for positive games additivity. This is a little bit strange, but this would be a way to characterize the core on balanced games if you don't want to change the society. So I have time now. But I'm almost finished. So the next thing that I do is to introduce a property that came into my mind, which is related to superadditivity. I remind you, superadditivity requires that the sum of the solution of two games is contained in the solution of the sum of the two games. And I should like to define something like the opposite property. So I should like to ask myself, when has X to be in the solution of the game? And I do it as follows. So compare what happens if I add solutions of another game. And the other game should be positive itself. So W is positive, and also V plus W is positive. So only this is what I do. And then I ask myself, what happens if I take an arbitrary element of the solution of W and add it to X? And if it's the case that X plus Y belongs to the solution of the sum of the two games, in all these situations, then X must be an element of the solution. So this is basically the converse. If you enlarge the class of games, so if you look, for instance, at all games W, then this is too weak. It doesn't. So then only you receive sigma V. So it doesn't work. So you need some a little bit stronger property, and we found out that the best what you can do is you require that for all games, not the zero games also, if you also allow the zero game to be in the class of games under consideration, then that have to be considered here, then it becomes too weak, so it's not strong enough. So you exclude the zero game, and you only look at positive games for comparative reason. And for all positive games that add up to a positive game under consideration, you receive that if you add X to a solution element, so X plus sigma of W is contained in sigma of V plus W. If this is true, then X must be a solution of the game. So this is used. We could not do more. I would have liked to do a little bit more, but I didn't see how to restrict further the set of games. So if you restrict it, it becomes stronger, but I couldn't find something that is working in this context. So it's a little bit artificial, I must confess, but it is something like the inverse of superadditivity. Therefore, I call it converse superadditivity. And if we have this, we have another corollary. So if we have the blue axioms that I mentioned right in the beginning, if we have also superadditivity and converse superadditivity, then we receive the core for each class of games that contains a positive game. So this is the big advantage. You can take each class. The only restriction is that the positive games, a small class of positive games, must be contained in gamma. Then this characterization works. But we have again this strange axiom that you need additivity on positive games. This cannot be avoided. If we want to avoid this, my idea was a different one. So let me explain what is reasonableness. So we denote by small b max I the maximal contribution of a player. What is the contribution of a player to a collision? This is what the collision gains if the player joins the collision. V of S to I minus V of S. The maximal contribution is the maximum of these numbers. Similarly, the minimum contribution is the minimum of these numbers. So, for instance, for convex games, the minimum contribution is Vi itself. For convex games, the minimum contribution is Vi. But for general games, we don't know. So, for convex games, for instance, this requirement means individual rationality. So it's a generalization, a weakening. It's a weakening of individual rationality. So it's weaker than, so to require that that player I receives at least his or her minimal contribution is weaker than requiring individual rationality. And the other thing from above, this was introduced already by Milner in 52, so this is also used in some axiomatization. So reasonableness. And then we generalize reasonableness to collisions. So here we have reasonableness for a single player, and now we look at the maximal contribution of a collision. T is a collision. The definition is the same as before. So we look what happens if the collision joins another one. So this is a contribution of the collision to the collision S. We look at the maximum. This is the maximum contribution of collision T. Similarly, the minimum contribution of collision T. Let me say, like here, you say the solution is collision-wise reasonable from above. If for each collision, each member of the solution, X, the member assigns to the collision at most the maximal contribution of this collision, and it's collision-wise reasonable from below if it assigns at least the minimum contribution. It's quite intuitive. I think it's quite intuitive that no collision should receive more than it can contribute. No collision should receive less than it always contributes. I think it's quite a reasonable, justified assumption. And then we can characterize the core. Almost each class of game need to make it big for unanimity games, so we require that for unanimity games each player can receive the unit. We require super additivity, and converse super additivity, of course. This is a little bit, this is well understood, this is almost well understood, and these are mathematical properties. So I don't see that super additivity can be motivated by fairness reasoning. Mathematical properties, but we are used to it. So Shapley value satisfies even additivity. So we are very much used to these mathematical properties. Scale covariance is, without any discussion, this is widely accepted. Scale covariance is widely accepted. And then reasonableness from below. So if you think that it's an intuitive property, then this is a reasonable axiomatization of the core. And the question is, what about reasonableness from above? And, this also works, but you remember that we defined the solution automatically. The solution cannot assign more than V of n to the entire group of pairs because V of n is a bound that is given. So this is the matter of the solution. Therefore, if you do it from the other side, if you don't have efficiency, then the players can receive less than V of n. So this is possible. Reasonableness from above allows to give them less than V of n. So we need efficiency in order to guarantee that. So these are dual properties, so to speak, and they should be replaceable, but this is not replaceable because we have the additional property that x of n is less or equal to V of n. This is in the definition of the solution. Therefore, we need efficiency in this place. So this is what I wanted to tell you, unless, yeah, this is what I wanted to tell you. Thank you.
Thank you.
Thank you.
Peter, the properties in theorem B and C are independent? Or
Yes, all property. Yeah, this is always, I don't know, n must be maybe bigger than 3, maybe I think 3 is enough. So the number of pairs must be 3. If it's too small, then you need less property.
Okay.
Even it's easy to find examples that show that this is not difficult. I mean, the result is not difficult. Only the idea. The question is the idea to define converse superadditivity like we did, or is it acceptable to have a property like reasonableness? This is the question. So if this is true, then it's fine. Otherwise,
Reasonable has been used to characterize the core before.
Reasonableness for person has been used, but reasonableness for collision-wise reasonableness has not been used, has not been introduced.
By for players, yes.
Yes.
Okay, thank you.
Yeah.